presenter, Professor Elin Kontis, Professor of Chemistry actually at the Eastern Michigan University in USA. And she's going to talk about community-based, community-based STEM experiential learning, and is it STEAM? Okay, let's see.
Okay.
Next,
Back and forth. Okay, this never works for me. Good afternoon, everybody. Thank you for being here. I know it's late in the day and it's a beautiful day outside. I'd like to continue the discussion. The question was, is it STEAM? What is STEAM? And we heard a lot of articles this morning about definitions of what STEAM are for one person, for another. What is it really? I don't think we know. I think we all take it differently, which is okay. And most of us start on the STEM side and then talk about adding, quote, the arts, whatever that is, to kind of enhance STEM. Wrong side, see? Yeah, kala. No? Stuck. Should work. There we go. Oh. Which end? Okay. Okay. I'm going to briefly talk about 5 items today, kind of and explain what I consider STEAM to be in terms of how various projects that we've done and how projects that other people have done have actually added to this. First of these is called the Innovation Core. In the United States, it's sponsored by the National Science Foundation, and it actually allows you to prepare a product and then sell that product, okay? Because most of us in STEM don't think about that. What we think about is, okay, I've got to do research, I've got to publish a paper, I've got to present at a conference, and that's it. So that was an interesting experience that we had, especially me, coming from academia. But I'm going to talk about the project called CSIE. It's a program that I founded and we've been working on for the last 14 years or so to actually involve our undergraduate college students so that they actually are retained and want to graduate. And how, in fact, the kinds of experiences that we offer them incorporate not only the science content, but also the idea of what you might call art. I use that term very loosely here. Then I'll talk a little bit about online chemistry. In order to accomplish this, to kind of get other people involved, other students involved who are not science or STEM majors, what we want to do is to actually engage them as well. And what kinds of activities are we going to need to do that? Okay? And then, in addition to learning about the content of STEM, especially our undergraduate students who are juniors and seniors need to know about what's next. They've learned all the chemistry or biology, they've gone out and they've done research and they've published papers. Now what do? They need to learn about what we call the soft skills, and we'll talk a little bit about that. And finally, there's a new wave of different kinds of competition. You may have heard of computer scientists and talking about hackathons, where they actually kind of bust into systems to see if they can hack those systems. Well, there's also something, the opposite is to solve problems, and solve problems on a global scale. So this Innovation Core, as I said, is a National Science Foundation project. It prepares scientists like me and engineers to extend focus beyond the academic level, beyond the area of working at a lab or so. It's based on teams. I was the principal investigator as the academician. We had someone from a startup company who was the entrepreneurial lead, and then we had a mentor from another university, in this case the University of Michigan, and so the 3 of us then got together to look at a product, understand how, set up a business model, how do we go out there and get customers and all of that stuff. Very short course, 7 weeks in duration. We had to do all kinds of things that normal businesses do that I didn't know anything about. Customer service, actually go out and actually interview at least 100 different possible customers. So that was a difficult thing, especially for me to do. And what we worked on is a product, and that's really what we did as well, is to take the product and see if it's marketable, and then actually go out there and do it. It's called the Gulliver Innovative Learning Process, GIL, and we were Team 494. And what this was smart education with learning analytics. I am not a person who works at the K-12 level. So that was a new experience for me as well. And we wanted to understand the analytics, that's where the computer scientists come in, and we wanted to work with teachers. So smart education is this. It's just systems that information and communication technologies are applied to collect data. So we had kind of streamlining online, live data being collected for actually the students that we were working on as our guinea pigs. They loved it. They actually saw things changing on a graph, and these were junior high students. They didn't necessarily have statistical analysis or any of that stuff under their belt. The other thing is that we wanted to merge both the smart education and what's called kinesthetic learning. It's just active learning, and what we mean active is that students actually get up and run around the room, and as they're wearing things like smartwatches or computers hanging around their neck, they can actually do all kinds of things, and all of that stuff is actually live and presented on the board as they do this. So the idea of smart education, again, this was all new to me. The Internet of Things and wearables, basically your smartwatches, your computers, your this, your that. Learning analytics, somebody did the computer programming for us that was live, and then we actually then developed the kinesthetic learning activities. So the sample activity, here's one example, but our famous one is actually Play Flu, in which students we give them certain watches to wear. Some of them are infected with a disease or a cold or a flu. Some of them are vaccinated. Some of them do not have vaccination. And then we let them loose in the room, and they kind of see if they can destroy other people by actually getting their virus to other people. And then we collect the analytics. And so that's basically what that was. This is another example in chemistry where the students are H's or O's, for example, and they run around, and if they get close to another person, they can actually build like an H2O molecule. So if you're talking about covalent bonding, that's how the students did that as well. So that was really fun to watch them do that. So what are the challenges? Well, you got to get the customers. Who are the customers? We thought they would be high school science teachers. We thought maybe they're middle school teachers, and these Play Flu examples are what we did with middle schools. Are they elementary school teachers? Remember, most elementary school teachers don't like science, unfortunately, at least in the United States. They kind of dread it and would rather do things like language, arts, and humanities and history. Did we go to hands-on museums? Yes, we did. We were in Washington, D.C. and went to the national museums there, and they loved it. They liked the idea of incorporating both the science and this idea of kinesthetic learning. And also university science professors. Do they want to have students running around in their classrooms? Not so much. So this is us at one of the national museums in Washington, D.C. We also connected up with Samsung and Intel. That's our team. And so we did a lot of running around. So that was fun to do. And we learned a lot. So it's taking product, moving it to reality. And what other kinds of things did we learn from this very quickly were things called pivots. We thought that it would fit elementary schools and informal learning environments, and they did because the museums liked it. But it's not just science activities. This type of activity can actually expand into other areas as well. Activities in literacy, for example, in math, in doing science, in doing mathematics, history, and that kind of thing. So it's valuable, and the model that we built was a good model that can be used elsewhere. That's part of STEAM. The second thing is the creative or CSIE project. Again, we wanted to bring in students to the university level and actually retain them so that they would really get geeked and actually graduate with a science or STEM degree. So that's CSIE. So it incorporates all the different kinds of sciences, but involved in that and embedded in that are also some of what we call, again, the arts. So let's look at that. Our model, our logic model, is based on the idea you can't just take students and fix them. You also have to fix faculty, so that faculty want to get together with other faculty, not just in the sciences, but in other places like philosophy, like education, like history, those kinds of things as well. And then through all that, we built these experiences, and that's called the CSIE. We found in Michigan, where I come from, at Eastern Michigan University, Southeast Michigan, we're really looking to build a STEM workforce because there are jobs out there. and students want to come into school, get trained, and be able to get a job. How do you do that? You have to give them some experiences. They can't just sit in a lecture or a lab and do canned experiments or learn all the theory. You've got to get involved with humanity. And that means you've got to get involved with companies, with NGOs, with all kinds of things. So we built these models, and we kind of went out and reached out to all these people. We've set up what are called STEM communities of scholars. Some of them actually live on campus together. We're also a school of about 22,000, very similar to Northeastern. And then we were thinking, and our next steps are then to kind of build this into a whole STEM area, or workforce, or hub, as they call it. Again, our ideas here are based on outcomes, outcome-based instruction, hands-on or experiential learning. Students get out there and investigate, they talk with each other and with faculty and with businesses, and then they're connected to other inquiries. So it's not just, I'm going to learn chemistry and I have no idea what chemistry does. So we kind of try to connect all this. So we've built a bunch of experiences. If you look at some of these, pointer, okay, if you look at some of these, here, for example, we have scientific presentation. In this particular course or experience, what we do is take students. They don't have to be science students, but it's good if they are. But we have students who are English majors or writers. They come in, we teach them communication or interview skills through our communications department. Then they go out and shadow scientists as one of our partners. They go back and then they interview that scientist, and then they build a video podcast. So that's an example of what I call sticking art into STEM, where it teaches them something other than the actual content. That's one of them. Ethics of genetics is another. Again, a combination between biology and philosophy in terms of how they operate. And I think there's one more that I like. Anyway, one deals with, and I'll show you an example in a second. But we try to do that since we're doing experiential learning, and we try to do that with each of our courses. We have what's called an academic service learning component, where we reach out with people, to others to help us out in this. And the other companies and businesses have been very, very supportive of this. Here's one. Cyanobacteria is a toxic bacteria. It's found in one of the lakes outside of the university. We go out there, we actually get the water, bring it back, and actually do some sampling. And we partner with, we partner with the Huron River Watershed Council. It's a nonprofit organization. We work with health and public health environment, so that means we have to deal with people that are not chemists, who are doing more social science work. This is fun course, Scoop on Poop. Go out into the fields where there's a lot of cows and see what the effect is of those cows dropping their whatever onto the soil, which then goes down into the groundwater, and if the groundwater is affected. So students love to do stuff like that. Here's the scientific presentation. We've worked with several companies. One of them is the NOAA, National Organization, Aeronautical and whatever. It's the weather people. We've done that. Universe with NASA. We connected up both the sociological, anthropological aspect with physics, astronomy, and also with biochemistry. Meals on Wheels is another one that we've done to connect both computer science, the people who work to take food to people who need it at a certain time, so we've optimized some routes for them. And then this last one is indicator. You go out in the middle of winter and count little flies by the water. And that helps the Friends of the Rouge River, which is the big river in southeast Michigan. The reason we do this is, of course, to actually help students get jobs. If they get the experience, they get the jobs, they're good. Southeast Michigan in the United States is where the car companies are. The auto companies, the big manufacturing companies are there. And now we have other companies, things like Electrobit, which is a global company out of Germany, who actually does cybersecurity on the software of autos so that somebody can't hack into an automobile, and as you're driving, somebody takes control, for example. Argus is another company that's local there. Bosch, big company. Cayman Chemicals, and then we have the NSF International that we work with. So we're trying to make those connections as well. These people are coming in and they're actually helping us develop curricula, and they're working with us to solve real problems. They build teams from our students and they work with them until they get an answer. So that's what that program is about. Then we have online chemistry for non-science majors, and that's basically all I'm going to say. A lot of people are doing online chemistry, for example, because that's really what students want. They want to be able to chime in from any place around the world. And this is primarily for students who, for example, are communications majors, returning nurses, political science, journalism, environmentalists. So again, we get a lot of different perspectives in how they do this. Soft skills workshops, we're all aware of that. In order for us to be here, we've had to understand and learn these soft skills, which include things like career planning for our students, communication, and that's extremely important. How do we talk to a person who knows nothing about our science? Publishing, of course, and grant writing are also important. How do you do that? We're all taught to do the research, but we're not necessarily taught on how to write it up and what to do with it later. So this is what I call, it's a world map, and the lighter spots here are where a lot of research centers are. And so we see, of course, the United States, we see in South America and the Brazil area, they're big on research centers. Of course, Europe, several pockets in Africa. India, of course, is a very large research-based center, and so is China. There's some going on in Australia down at the end here near Melbourne. And so those are important. That means that people are working on a global basis. Global basis. So not only do we need to talk to each other in the lab, we need to be able to communicate out to the world. So these are just some things. For example, I'm an engineer. I'm doing research to produce faster and better computers. So we teach our students simple phrases, elevator speeches. Somebody will say, your grandmother comes up to you and says, okay, what are you doing in school? If you start talking about molecules and all that stuff, like, no, unless the grandmother is exactly in your field of work, okay? For example, I'm an artist and I create using many types of materials. I'm a chemist, I'm discovering drugs. So this kind of communication is also important. I'm a high school teacher and I prepare students to major in sciences, those kinds of things. I'm really going fast. So communicating science is important, and it depends on where you are. What's your audience? We know that if you publish research results, you're going to talk in one fashion. Presenting your results at a scientific meeting means you have some communication skills, interacting with students. Now, discussing your research with the public is not things that we're trained to do as scientists, but we need to do all that stuff. How about our neighbors? I happen to be an radioanalytical chemist. My neighbors are concerned. They tell me laughingly, ha ha ha, you were at the reactor, are you going to glow tonight? You know, that kind of thing. So you have to kind of be able to discuss all that stuff. And then, of course, policy, as someone talked about this morning, meeting with elected officials. You know, you have to know how to talk to them as well. Most of them have not had science. So here are examples of performance, art, if you will, embedded into a periodic table of chemical elements. These are students from University of Mexico, Hidalgo University in Mexico, and they've built life-size elements in big crates. They have a lot of information on them. They consider it the largest periodic table of chemical elements in the world. And what they do is when they do this, set this up, they also put costumes on to represent different elements. And so this is part of the group there. So they're excited to do that. They're engaged, and everybody sees that. The young kids love it. This happens to be another example of students. These are high school students from Islamabad, Pakistan, and they were part of this first, part of this first global team that started. They actually were allowed to go to a place. They came to Washington, D.C. with a lot of other people from a lot of different countries, and they actually were given a robot kit, and they had to then decide what to do, how to build it themselves, high school kids. And then this robot had to cross this bridge, and then the blue balls are water, and the orange balls are contaminants in water. Their robot had to actually pick out and separate the blue balls from the orange balls. And so they happened to win in this particular contest. So that was exciting for them. The youngest one was, I think, about 14. And finally, the idea of thinking competitions. Okay, thinking competitions are what are called solve-a-thons. MIT is big on this. They've actually branded this name. But they allow you to actually come up with the idea of being part of the solution. So we did this on campus, and we had several issues, general issues. They could be scientific or not. And so groups of students would sign up, and they actually worked with things like opioids, big problem in the United States, obviously. Water contamination. We happen to be near Flint, Michigan, which their water was totally contaminated. A lot of issues there. We also looked at workforce training. What does that mean? A student wanting to become somebody. And then actually on campus dealing with the education. So these were very global issues. Teams came, and they weren't all STEM teams. They were people, we had people from the community come who were in the social services who actually came and actually became part of this thinking competition. Teams, they came up with final solutions, and they were judged, and they got iPads, those who won. Okay, so that's just another example. So here we have, what does that look like to you?
More power to everybody.
It's kind of a plane, yeah, okay. Again, this was a group of students from MIT. They got money from United Technologies, and they built a plane with materials. So here we're talking chemistry, plastic, that kind of thing. We're also talking physics, engineering, obviously, and we're also talking about the name of this plane, which is called Daedalus. Do you know the story of Daedalus and Icarus? It's a myth, and so we've incorporated all of this art. Daedalus and his son Icarus were stuck in the Minotaur's, what's it called? Whatever, in Crete. Labyrinth, thank you. And they were collecting feathers from the pigeons and birds who were flying out. They couldn't get out. And also wax from their candles and so on, because he was the architect of this labyrinth, and the king said, "Nuh-uh, he can't go someplace else and rebuild this, so he's stuck in the labyrinth and he can't get out." And so what he did and his son collected all this stuff and actually engineered wings, and they took off, and that was great, wonderful, terrific. The son, however, was really, hey, I can fly high to the sun. Unfortunately, he flew too high to the sun, and the sun started melting the wax on the feathers, the wings, and he fell. And where he fell in the Aegean Sea is called the island of Icaria. So we have all kinds of art here involved with all kinds of stuff. So that's my story. Okay, thanks.